These two pieces of code do exactly the same job. One finishes in under a second, the other takes 3 hours. And here's the uncomfortable part. They look almost identical. The difference comes down to one idea: Big O notation. And most tutorials explain it backwards. In the next 8 minutes, you'll be able to look at any piece of code and name its Big O. No math degree required. And you'll dodge the counting mistake that fails real interviews. Let's make it click. Here's the mental shift. Big O is not about how fast your code is. Speed depends on your laptop, your language, even your battery. Big O asks a better question. When the input gets bigger, 10 items, 10,000, 10 million, how much more work does your code have to do? It measures growth, not speed. That's the whole idea. Everything else is detail. You're hosting a dinner party. Some jobs don't care how many guests come. You turn the oven on once, whether it's 1 guest or 100. That's constant work. O of 1. Some jobs grow with the guest list, 1 plate per person. 100 guests, 100 plates. That's linear, O of N. And some jobs explode. If every guest greets every other guest, 10 people means 45 handshakes. 100 people, nearly 5,000. That's O of N squared. Same party, like 3 completely different growth patterns. Code works exactly the same way. So how do we find the Big O of real code? We count steps. This loop touches every element once. 6 items, 6 steps. Double the array, and the steps double with it. The work scales 1-to-1 with the input, so this is O of N, the linear time. Notice what we didn't do. We never asked how many milliseconds it takes. We only asked how the step count grows when N grows. That's the skill. Real code is messy. Maybe your function does 3n squared steps plus 5n plus 20. Big O throws almost all of that away. Why? Watch what happens as N gets huge. At 1,000,000 items, the N squared term is doing 99.9% of the damage. The rest is a rounding error, so we keep only the fastest growing term and drop the constants. Big O is deliberately blurry, and that's its superpower. Here's the whole family on one chart with real numbers for 1,000 items. O of 1, a single step always, like grabbing an array element by index. O of log n, about 10 steps, having the problem each time like binary search. O of n, 1,000 steps, 1 look per item. O of n log n, 10,000. The signature of good sorting algorithms. O of n squared, 1,000,000 steps, nested loops over the same data. And O of 2 to the n, at just 1,000 items, more steps than there are atoms in the universe. This chart is 90% of what interviews expect you to know. Now let's read Big O straight off real code in Java and Python. Grabbing one element by its index, AR, at 500, is a single step no matter how big the array is. O of 1, a loop that touches every element once. Summing, searching, printing. Grows step for step with the input. O of n. One glance at the structure tells you the story. No loop over the data, constant. One loop, linear. A loop inside a loop, checking every pair for duplicates, multiplies the work. 6 items, 36 checks. 1,000 items, 1,000,000. Nested loops over the same data almost always mean O of n squared. Now the beautiful one. Binary search throws away half the remaining data at every step. 16 items take 4 steps. 1,000,000 items? Only about 20. Whenever an algorithm halves the problem each round, that's O of log n. And it's why sorted data is such a big deal. 3 mistakes that cost people interviews. Number 1, 2 loops, one after the other, are not O of n squared. Nested means multiply, sequential means add. N plus n is 2n, and we drop the 2. Still O of n. Say it in an interview and you'll instantly sound like you know what you're doing because loop structure, not loop count, is what matters. Number 2, hidden loops. This line looks innocent, but in on a list secretly scans the whole list, one element at a time. Put it inside another loop and you've built O of n squared without ever typing a second for. This is exactly why hash sets exist. The same check against a set is O of 1. One keyword, 1,000 times difference. We built that intuition in the hash set episode. Number 3, quoting your lucky day. Sure, linear search might find the answer in the first box, but Big O describes the worst case. The target hiding in the last box or missing entirely. When an interviewer asks for complexity, they mean the guarantee, not the good luck. If you want credit for the average case, name it explicitly. Precision here is what separates memorizers from engineers. Quick interview tip: never wait to be asked. The moment you finish writing a solution, state its time and space complexity out loud. This is O of n time, O of 1 extra space. Interviewers are trained to listen for it, and volunteering it unprompted is the cheapest credibility you will ever earn. Let's lock it in. Big O measures growth, not speed. Count the steps, keep the fastest growing term, drop the constants. No loop, O of 1. One loop, O of n. Having, O of log n. Nested, O of n squared. Sequential loops add, hidden loops multiply, and Big O always tells the worst case story. That's genuinely all you need to read the complexity of most code you'll ever meet. Next, watch these ideas race for real. 5 sorting algorithms, 1 array, animated start to finish. It's on screen now. And if this finally made Big O click, subscribe. Code clarity, data structures, explained visually.